Hi everybody, welcome back to College Algebra, and today we're in section 2.6 and we're going to be looking at some graphs of some basic functions. We're going to talk just a little bit about continuity. I'll give you kind of an informal definition and we'll talk about that. And then we're going to look at the basic graph for several different kinds of functions. We'll look at the identity function, the squaring function, the cubing function, and then the square root function and the cube root function, and also the absolute value function, and we'll also take a look just for a second at the greatest integer function. So here we go. So first, let's get an informal definition for continuity. A function is continuous over an interval of its domain if its hand-drawn graph over that interval can be sketched without lifting the pencil from the paper. So in other words, the graph should not have any holes in it or breaks like a vertical asymptote. If a function is not continuous at a point, then we say it has a discontinuity at that point. So here are the graphs of a couple of different functions. You can see in the graph on the left we have a parabola, and you can see that you could draw the entire thing without picking up your pencil, and therefore this graph is continuous on its entire domain. It is continuous on the interval negative infinity to positive infinity. And that means that from x equals negative infinity until x equals positive infinity, this graph is all in one piece. This second graph, on the other hand, has a hole at x equals 3. In other words, it has a discontinuity at x equals 3. So this function is continuous on the interval from negative infinity to 3, and then once we get past 3, it's continuous again, so from 3 to infinity. So we would say this graph is continuous from negative infinity to 3, and notice the parentheses there, and from 3 to infinity. We don't need the union symbol here because we're not trying to join these two intervals together. We're just saying that the function is continuous on this interval and also on this interval. Now let's look at the identity function, which is just the basic function f of x equals x. So whatever you plug in as x, that's what's going to come out as the y value. I'm going to choose just some x values for us here. Let's go ahead and use all the integers from negative 2 to positive 2. When x is negative 2, of course, y is also negative 2. When x is negative 1, y is also negative 1. That's what the identity function does. Whatever you plug in as x comes out as y. So watch what happens when we graph these points. Negative 2 will be here. Negative 1 will be here. 0, 0, then 1, 1, and 2, 2. So you can see that the graph forms a straight line that goes through the origin. Let's go ahead and get this information for this function. The domain is going to be from negative infinity to positive infinity because you can see that any number can be plugged in for x, and you can also see on the graph that the graph stretches forever to the left and to the right. So the domain will be negative infinity to positive infinity. The range is the lowest y value to the highest y value. So you can see that the lowest y value we can get from this graph is going to be negative infinity, and the highest y value we can get from this graph will be positive infinity. So that's the range, negative infinity to positive infinity. This graph does not have any discontinuities, so we would say it's continuous on its entire domain. So we'll say it's continuous from negative infinity to positive infinity. And it's always going uphill, so we'll say it's increasing on the interval from negative infinity to positive infinity. All right, now let's look at the squaring function. And just the basic squaring function is f of x equals x squared. So again, I'm going to choose all the x values from negative 2 to positive 2, and we'll just plug those in here and see what we get for y. If you plug in negative 2 for x, negative 2 squared is going to be negative 2 times negative 2, so that's positive 4. If you plug in negative 1 for x, negative 1 times negative 1 is positive 1. 0 squared is 0, 1 squared is 1, and 2 squared is 4. So when we graph those points, we get negative 2, 4, negative 1, 1, 0, 0, 1, 1, and 2, 4. So you can see it forms what we call a parabola. Now look at the equation for the function. So this is a polynomial function, and therefore the domain is going to be negative infinity to positive infinity. You can think of domain two different ways. Remember, one way we look at domain is it's all of the numbers that can be plugged in for x that will give you a valid y value. And certainly you can see here that any number you plug in is going to be able to be squared. But also look at the graph. This graph is continuing forever to the left, and it's also continuing forever to the right. So as we plug in x values, -3, -4, -5, and so on, you can see that we'll get larger and larger y values, and the graph will continue to move out this way. And as we plug in larger and larger x values, the graph would continue to move out this way. So that's two different ways to determine that the domain is negative infinity to positive infinity. Now the range is the lowest y value to the highest y value. And you can see from the graph here that the smallest y value this graph is ever going to give you is 0. So we would say that the range goes from 0 to infinity. And notice that we need a bracket on the 0 here because there really is a point on the graph where the y value is 0. This graph does not have any discontinuities, so it's continuous everywhere. So we'll say it's continuous on the interval from negative infinity to positive infinity. And as far as where this graph is increasing or decreasing, you can see that the left half of the parabola is decreasing because the y values are getting smaller as we move to the right. But once we get to this lowest point, after that, the graph starts to increase. So notice that from x equals negative infinity all the way until x equals 0, it's going downhill, so that's decreasing. And then from x equals 0 until x equals infinity, it's going uphill. So we would say that the graph is decreasing on the interval from negative infinity to 0. And remember, we always talk about increasing and decreasing in terms of open intervals. So parentheses only, no brackets. So that's where it's decreasing. And then it's increasing on the interval from 0 to positive infinity. Now let's look at the cubing function. So again, I've chosen these same x values, and we'll plug those in here. So -2 to the third power would be -8. -1 to the third power would be -1. 0 to the third power is 0. 1 to the third power is 1, and 2 to the third power is 8. So we're just plugging each of these x values in here and generating the y values. Now when we graph these points, -2, 8 will be here. -1, -1 would be here. 0, 0 here. 1, 1 here, and 2, 8 here. And when we connect the dots that we've got here, we get a graph that looks like this. It's kind of like twisted in the middle. This is the basic cubing function. It goes down on the left side and up on the right side. Now, for the domain for this function, look at the function equation. F of x equals x to the third. So you could plug any number in here for x, and therefore the domain is negative infinity to positive infinity. The range is the lowest y value to the highest y value, and you can see that we never reach the lowest y value, and we also will never reach the highest y value, and so the range is also negative infinity to positive infinity. This graph does not have any jumps or breaks, so this graph is continuous on its entire domain from negative infinity to positive infinity. And now as far as where this graph is increasing or decreasing, a lot of people are tempted to say that it's decreasing here, but remember, we always have to think about increasing and decreasing in terms of what is the graph doing as we move to the right. So as we move from left to right, this graph is always going uphill. There's never a time when it's not going uphill. So this graph is increasing on its entire domain from negative infinity to positive infinity. Now here is the square root function, and we've got f of x equals square root of x. Now this time, because we're going to need to take the square root of whatever we plug in for x, I'm going to choose some different x values. So I'm going to choose -4, -1, 0, 1, and 4. And let's go ahead and plug those in. So if we plug in -4, the square root of -4 is an imaginary number, so we can't graph that on this coordinate system, so I'm not even going to write it down. The square root of -1 is also imaginary, but the square root of 0 is 0, and the square root of 1 is 1, and the square root of 4 is 2. So let's see what we get when we graph these points. These first two are not graphable, but 0, 0 is here, 1, 1 is here, and 4, 2 is here. And so this is the graph that we get when we graph the square root function. Now remember, domain is all the numbers that you could plug in for x that would give you a valid output, and in this case the smallest number we can plug in for x is 0, and you can see that the graph does start at x equals 0. So the domain of this function is going to be 0 to infinity. And we do have a bracket on the 0 because we can plug in 0. That's a valid number to plug in. The range of this function is also 0 to infinity. And you can tell because 0 is the lowest y value, but these y values continue to grow as we move to the right. It's going to go higher and higher. Although it's not going high very fast, it is continuing to get higher. So the range is 0 to infinity. This graph is continuous on its entire domain. Once it gets going, it doesn't have any breaks. So we would say this graph is continuous on the interval from 0 to infinity. And it's always going uphill as we move to the right. So this graph is increasing on the interval from 0 to infinity. But notice that whenever we talk about increasing and decreasing, we always talk about an open interval. So you won't see any brackets on the intervals where the function is increasing or decreasing. Now here is the cube root function, and as you might imagine, it's a little bit related to the square root function, but remember we can do the cube root of negative numbers, so we won't have that characteristic where the graph starts at 0. So let's go ahead and choose some convenient values to plug in for x. This time I've gone with -8, -1, 0, 1, and 8. Okay, so plugging these numbers in, the cube root of -8 is going to be -2. The cube root of -1 is -1. The cube root of 0 is 0. The cube root of 1 is 1. And the cube root of 8 is 2. Now let's graph those. Here we have -8, -2, -1, -1, 0, 0, 1, 1, and 8, 2. And when we connect those dots, you can see it looks a lot like the cubing function, but turned on its side. Notice that we can get the cube root of any number we plug in for x, so the domain is -infinity to +infinity, and you can see that here where the graph stretches forever to the left and forever to the right. And the range is also going to be -infinity to +infinity, because although the y values aren't changing very quickly, the y values will continue to get lower as we move to the left, and they'll continue to get bigger as we move to the right. So that's the range. And then this graph is continuous everywhere. It doesn't have any jumps or breaks, so we say it's continuous on the interval from -infinity to +infinity. And look at this. The graph is going uphill everywhere. As we move from left to right, the graph is always going gradually uphill. And so this graph is increasing on the interval from -infinity to +infinity. Now let's look at the absolute value function. So this time the integers that I choose for x are going to be back to the integers from -2 to +2. And let's go ahead and plug those in. The absolute value of -2 is +2. The absolute value of -1 is +1. And then the rest of these, quite obvious if you know what absolute value does. Remember, absolute value just turns a number positive. So when we graph these points, you're going to see -2, +2 here, -1, +1 here, then 0, 0, 1, 1, and 2, 2. And you can see that instead of forming that nice parabola shape that we had with the x squared function, here we get more of a V shape. It has a sharp corner at the bottom. So this is the graph of the absolute value function. Any number can be plugged in to this function, so the domain is from -infinity to +infinity. The range, though, only goes as low as y equals 0, so the range is going to be from 0 to infinity. Notice the bracket because we do have a point on the graph that has a y-coordinate of 0. This graph is continuous everywhere, so we would say that this graph is continuous on the interval from negative infinity to positive infinity. Now, part of the time this graph is going downhill and part of the time it's going uphill. So the interval where this graph is increasing is from 0 to infinity, and the part of the graph where this function is decreasing is from negative infinity to 0. Remember, we always state intervals of increasing and decreasing in terms of x values. So from x equals 0 to x equals infinity, we're going uphill. From x equals negative infinity until x equals 0, we're going downhill. And remember, we always talk about increasing and decreasing in terms of open intervals, so no brackets here no matter what. Now let's take a look at the greatest integer function for just a second. The greatest integer function is notated by these double brackets. And so when you read this, you say f of x equals the greatest integer of x. And what that's going to do is it's going to pair every real number x with the greatest integer that is less than or equal to x. And when we take a look at the xy table, this will become clearer to you. So now we're going to go ahead and generate the graph of the greatest integer function. And to do that, we need to make sure and choose some x values that are not integers. So I'm going to just choose several x values, a lot more than we usually do. And I'm going to choose x values that range from -3 up to 0. So now remember, when we plug a number into the greatest integer function, the way we calculate the y is we say what is the largest integer that is less than or equal to whatever we're plugging in. So if I plug in a -3, the largest integer that is less than or equal to -3 is of course -3. If I plug in -2.9, the largest integer that is less than or equal to -2.9 is also -3. And the largest integer that is less than or equal to -2.5 is also -3. And as long as we're plugging in -2 point anything, the integer that's less than or equal to -2 point anything is always going to be -3. But as soon as we jump to the next integer, which is -2, the greatest integer that is less than or equal to -2 is -2. So you see how the y value jumps from -3 to -2. Now as long as we're at -1 point anything, the y value is going to remain -2. What's the largest integer that is less than or equal to -1.2? Well, it's still -2. What's the largest integer that is less than or equal to -1.1? Well, it's -2. So we get all these -2's here, and I've only done 3, but imagine if we had -1.009, -1.007, -1.000002. All of those y values would be -2, and it stays that way until we get to -1 exactly. And what's the largest integer that's less than or equal to -1? Well, of course, it's -1. And now we're going to see the same thing here. What's the largest integer that's less than or equal to -0.8? Well, it's -1. -0.5, it's -1. And so on until we get to 0. What's the largest integer that's less than or equal to 0? Of course, it's 0. So when we go to graph this, here's what happens. We're going to have a point at -3, -3. But then any x value that's -2 point something is going to also have a y value of -3. So the graph just stays constant until we get to an x value of exactly -2. And at that point, the graph jumps up to a y value of -2. So to show that the graph no longer exists when we reach x equals -2, we need to put an open circle there, and then we put a closed dot at -2, -2. So this is telling you that as long as the x value is -2.1, -2.05, -2.0003, as close as you can get to -2, the y value will stay -3. But as soon as you get to x equals -2, the graph's going to jump. And then it's going to remain constant at y equals -2 until you get to x equals -1, and then it's going to jump again. And it's going to keep doing that. Every time the x value reaches a new integer, the y value is going to jump up one. So we didn't fill in the table enough to do all of these, but you can imagine that the pattern continues. So this is what the graph of the greatest integer function looks like. Now let's talk about the domain. Remember, domain is all of the x values that can be plugged in that will give a valid y value. Well, you can see that we can always determine the largest integer that's less than or equal to any number. So the domain needs to be -infinity to +infinity. And you can also look at the graph and see that every x value is represented by some point on the graph. There is no x value where the graph fails to exist. Now, what about the range? We cannot say that the range is -infinity to +infinity because there are lots of values in between the integers where the graph does not exist. There are no points, for example, with a y value of 0.5. There are no points with a y value of 1.7. So we can't say that the range is -infinity to +infinity. In fact, the range is -3, -2, -1, 0, 1, 2, 3, and we would continue to have steps that are larger than 3, and we would have steps that are smaller than -3. So what we're going to do, instead of stating the range in interval notation, we're going to just state the range in set notation. So I'm going to say that the range is the set ... -3, comma, -2, comma, -1, comma, 0, 1, 2, 3, ... And the dots indicate that the integers continue forever to the left and forever to the right. We also might have said just in words that the range is all integer values. Now let's think about the continuity of this graph. Well, you can see that at every integer value there is a break or a jump in the graph. And so instead of trying to state where this graph is continuous, it's actually easier for us to state where this graph is discontinuous. And we're going to say that this graph is discontinuous at all integer values. In other words, every time the x value is an integer, the graph has a discontinuity. Now we need to determine where this function is constant. Notice that we're not even talking about where the function is increasing. And that's because everywhere this graph is continuous, the y values are all the same. So we wouldn't say that this function is increasing, but we can say that it's constant on the interval from -3 to -2. It's constant on the interval from -2 to -1, and so on. And remember that when we talk about intervals where the function is constant or increasing or decreasing, we always refer to open intervals. So we'll just say that this function is constant on the open interval from -3 to -2, from -2 to -1, and so on. And again, we have the dots that indicate that those intervals continue forever to the left and forever to the right. Now, recognizing these basic graphs is really all that we are going to do in this section. So we talked a little bit about increasing, decreasing, and constant. We talked a little bit about continuity, and we learned these basic graphs. So you'll want to be able to identify the basic graphs and to determine the domain range and these other things. But as far as doing anything with the graphs themselves, we're not going to graph all kinds of different functions. You just need to be able to work with the basic functions that we've talked about, and that's it. So I'll see you guys again in the next section.